Okay, should be good.
Awesome, thanks. I'll just wait until we hit 2 o'clock. So, okay, it is officially 2 o'clock, so let's get started. Welcome everyone to the October edition of Rocky World's Discussions. I am delighted to introduce Maggie Thompson, who is our speaker today. Maggie is both at ETH Zurich in Switzerland, where she is currently located right now, but also affiliated with the Carnegie Institution for Science Earth and Planets Laboratory in DC. And Maggie will be telling us about the atmosphere interior connection in rocky planets, which is great. I'm so excited. Just to cover a little bit of practicality, we'll have Maggie's talk for about 30 to 40 minutes, and then there will be plenty of time for questions and for discussion. And just for a bit of netiquette, please use your full name on Zoom. Please keep muted throughout the talk. And at the end, if you'd like to ask a question, it would be great, if possible, if you could turn your video on as well. So with that, I will hand over to Maggie. I will stop sharing this slide and let you share.
Wonderful. Thank you so much, Anjali. I will get my slides up. Okay. Wonderful. Okay, hopefully this all looks clear for you. I just want to start by saying I really enjoy these Rocky Worlds discussions. So thank you guys so much for putting these together. And now it's really fun to be on the other side and tell you some of the things that I have been up to. And so today I'm excited to tell you about how we can try and understand volatile partitioning using both lab experiments and numerical modeling tools, and why this is really important to connect the interiors and atmospheres for rocky planets. So I'm going to break up my next 30-40 minutes into roughly 3 parts. So I'm going to start by asking the question, what actually controls the mass and composition of rocky planet atmospheres? And then I'll get into the experimental work that I've been doing, which is mainly right now focused on hydrogen solubility, but I'll also touch on how we can apply this sort of method to other volatile species, and also doing additional experiments to look at outgassing speciation. And then I will finish by talking about how we can combine these experimental works into numerical models to help us actually connect the interiors and atmospheres of planets, and particularly help us inform upcoming observations and observations actually that we already have with JWST. Okay, so just a brief review. This is probably quite familiar to many of you listening today, but there's a particularly exciting class of rocky planets that are really amenable to near-term characterization. And these are often referred to as magma planets. So these are planets that have extensive lava or magma oceans at their surfaces. They're quite close to their host star, so they have these short orbital periods, and that provides us with one observational advantage. And then the second is also that they have bright day-side fluxes in infrared light. These planets often tend to be tidally locked, so there's one side that is permanently facing their host star. And so these 2 plots here from Chow et al. 2021 show you the distribution of these low mass, rocky, and hot planets. So you're looking at, on the left, radius versus orbital period, and then on the figure on the right is radius versus mass. And you might recognize some of these magma worlds. In particular, 55 Cancri E has been observed recently with JWST, with some detections of different carbon species in the atmosphere, and many more are currently and going to continue to be observed with JWST. And these are exciting because they give us a window into rocky planets and what their atmospheres might be like. And they also can present us with an analog for also trying to think about the early Earth. When Earth in its early history had a magma ocean, these worlds give us a window into that earlier period in our planet's history. Okay, and so taking a step back and thinking about how rocky planets themselves form their atmospheres, in general, when we just think about planetary atmospheres, not even thinking too much about planetary mass, we can think of generally 2 main types of atmospheres. So first, there are primary atmospheres, and these form when we capture hydrogen-rich gas from the stellar nebula. This is the main mechanism by which the giant planets obtain their atmospheres. So thinking like Jupiter, this has a hydrogen-dominated envelope around it. And then there's also secondary atmospheres, and these form instead through outgassing during planetary accretion, and also process can continue through different tectonic processes. And so initially, when we think about low mass rocky planets, a lot of times we think about secondary atmospheres because we think these planets may not be massive enough to hold on to significant primary atmospheres. But recently, and also thinking about the distribution of planets that we have observed, where we see a lot of planets that are in between the size of Earth and Neptune, it's also important to think about these two scenarios not just isolated and it's either one or the other, but you could have more hybrid atmospheres. So these are atmospheres that form through a combination of both nebular gas and also outgassing from a planet. So calling them hybrid atmospheres here. And this could be important also for lower mass rocky planets, at least early in their evolution. Okay, now going back to these magma worlds, what ultimately controls the mass and composition of their atmospheres? So, of course, outgassing is important. So one of the key things that will control what these planets are made of is the rocky precursor material that actually went into building this planet. That will have a dominant influence on what species degas from the magma ocean. But another feature that's very important is thinking about how these light volatile species can actually dissolve into this planet's magma ocean. So we refer to this as solubilities, just thinking about how things dissolve into different media. And so one of the main ways that we quantify solubilities are using solubility laws. And so a simple kind of rough schematic version of what that looks like is shown here. So you can relate the mole fraction or the abundance of a particular species that has dissolved into your magma ocean to the partial pressure of that species in a planet's atmosphere. And so I want to say this is going to be the focus of what I'm going to talk about experimentally today. And also just to say that we still have a quite limited experimental data set on the solubility behavior of major atmosphere forming gases, particularly for a range of exotic magma compositions that could be relevant for exoplanets, because much of the experimental work that has been done so far, and rightly so, has been focused on thinking about the Earth. But now that we are discovering these exoplanets, we need to start expanding that compositional parameter space. And so just to show you what some of these solubility laws actually look like, this is a figure showing you the concentration of different volatile species that are color-coded in this figure from this is just sources from the literature, papers that date back from the 90s all the way up into the 2000s, and some that are just from a few years ago, looking at different volatile species, how much of those species can dissolve into a melt in parts per million. And then as a function of the fugacity or partial pressure of these species in the gas phase. So something that you'll notice, for example, water and sulfur, the blue and green curves here are very, very soluble, whereas something like methane, the pink curve, is less soluble. But I want to point out something that's sort of hidden in this figure here is a lot of other factors that can affect the solubility of a particular species. So that can include things like the temperature of your surface, your magma ocean surface interface. Again, the composition of your melt can vary this, the redox state in your atmosphere, and also potentially the presence of other volatiles. And so the title of this talk was Inside Out, and I felt like I would be a bit remiss to not include a little Inside Out reference. So I have to admit I have not seen the second Inside Out movie, but I have heard that they have a new emotion in this movie, which is anxiety. That's represented by this little guy here. So this might give you some anxiety to think about all these different factors that can influence your solubilities, and how are we supposed to incorporate these if we're actually just trying to interpret, say, atmospheric observations from JWST. So what I would like to do today is hopefully convince you that we don't need to be too anxious. There's ways in which we can account for these different factors and see which factors actually have a strong influence compared to others. And so hopefully you'll start feeling more like joy when we think about solubilities in magma worlds. Okay, and so there's a lot of different volatile species that we could focus on. But one of course, the most abundant element in our universe, and one that seems like a good place to start, would be to think about hydrogen. And I'd like to take a few moments just to motivate why we want to think about hydrogen and why its solubility for rocky planets can be important. And so if we think about terrestrial planet formation in the planetesimal accretion scenario, we have planetesimals accreting to form planetary embryos. And if these embryos and as they grow, accreting planets can form nebular atmospheres, this can be possible if their planetary mass is large enough. And in such a scenario, you will be hot enough for various with various sources of heat, including just resultant heat from formation and also decay of radioactive nuclei that can cause the planet to have a magma ocean. And so when you have this magma ocean overlaid by a nebular atmosphere, you can have ingassing that occurs, and this could be a source for dissolving hydrogen into the planet. And this has become a topic that even recently has sort of been looked at again in trying to think about the source of Earth's water. So in a recent paper by Ed Young and others last year, they thought about a scenario in which Earth could have acquired all of its water from ingassing of a nebular atmosphere. So again, this requires that the planet mass be large enough at the time that it has, that there's still nebular gas in the protoplanetary disk, but that you could dissolve this hydrogen into a magma ocean. And then there are subsequent chemical reactions that take place between oxygen that's in your magma ocean from all of your different silicates and composition of your magma, and that reacts with the hydrogen that was dissolved. And then later, over subsequent cooling, this forms water, and that can condense out and be the source of water today. Now, there's still questions here, and I would love to discuss this, of course, at the end. But so this motivates thinking about this for rocky planets. And briefly, I also want to mention that hydrogen is important in thinking about the abundance that we see of subneptunes. So not just thinking about low mass rocky planets, but also going into slightly, into larger planetary sizes. So we have this distribution. This figure on the left is the sort of famous, looking at the radius valley, where you see this distribution of planets that have periods less than 100 days. So we have this distribution of super Earths and sub-Neptunes. And one of the things that's very interesting when you look at this distribution is that while the most abundant type of planet that we see here are these sub-Neptunes that have sizes around 2 Earth radii, there's a really steep drop in planet abundance above 3 Earth radii. And that's been termed the radius cliff. And so one potential explanation for this radius cliff could have to do with hydrogen solubility. So in 2019, Edwin Kite proposed this idea of a fugacity crisis, which is in a scenario where you are accreting and gathering enough nebular gas on a growing proto-sub-Neptune. If you reach the size of around 3 Earth radii, that results in a surface pressure where you have your magma ocean overlaid by a thick hydrogen envelope. At that point, the solubility of hydrogen increases significantly. And this is also due to the fact that you are now at such high pressures that you have to deal with non-ideality, which I will also discuss a bit later on. But essentially, then this increased solubility of hydrogen draws this down from the atmosphere, and then it basically inhibits further growth of the planet. So you can't just keep growing these planets more and more, and instead you see this decrease in abundance. And so this suggests that, again, hydrogen solubility, particularly thinking about the distribution that we observe of super Earth sub-Neptunes, is also quite important. Okay. So what do we know so far about hydrogen solubility? So there's been a series of studies done, and I'm just showing several here. This is not a fully comprehensive list. But again, what you're mainly looking at is trying to understand how much hydrogen you can stick into a particular melt under a range of conditions. So under different temperature, pressure, redox state, and melt compositions. So a lot of the prior hydrogen solubilities experiments that have been done have been conducted under several gigapascal conditions and for temperatures that are similar to what is relevant for like Earth-like mantle compositions. And so one of the things that is still missing is data for compositionally diverse melts that are unlike what we see for for modern Earth, and also for a range of pressure conditions, both the low pressure end and also the higher pressure end, getting into several GPa. And just to show you mathematically, what some of these solubility law formulas look like, again, you're really just often relating the amount that you can dissolve of hydrogen, so in this case in parts per million, to the fugacity or partial pressure of that species in the gas phase. And so what we have sought out to do is to gain a deeper understanding of hydrogen solubility. We're focusing on the low pressure end. So this is relevant to if we're thinking about something like early Earth, how it could be accreting and in-gassing some of this hydrogen. And so I will now get into those experiments. So we've done a series of 1-bar hydrogen solubility studies using a fairly classic technique, just using a gas mixing furnace. So this is a system that allows you to mix various proportions of carbon dioxide and hydrogen gas at temperatures from anywhere from as low as 1,000 all the way up to 1,600 degrees Celsius. And so inside of this furnace, this is a picture of what the setup actually looks like at ETH. You can suspend various silicate samples. So in this figure on the upper right, you're looking at 5 different compositions. They all look very similar, but I promise they're all slightly different. And so they hang by this little chandelier. And then you lower them into the furnace. They're at the hot spot, so they're at the temperature that you have set the system to. You set your gas composition. So this we can explore a range up to pure hydrogen, so 1-bar hydrogen gas to different proportions of hydrogen and CO2. And then after the system has equilibrated, we quench the experiment. So we essentially want to cool this system as quickly as possible to preserve this melt composition as best we can. And so we end up sending a voltage through this system. It cuts burns the wires here, and then they drop onto a copper plate. And so then we end up as this bottom image on the right shows, with this nice quenched glass sample that we can then analyze to measure in this glass how much hydrogen has dissolved into the system. And so I know that tables in presentations can be super annoying, and this one has small font, so it is not something for you to look at in a lot of detail. All that it is to show is that we're focusing on melts in the C mass or calcium, magnesium, aluminum, silicon system. In some of these cases, we've also added iron. So we are varying the proportions of each of these components systematically, so we can also try to get an understanding of the effect of melt composition on hydrogen solubility. And again, we looked at a different range of gas mixtures. So this is constraining the redox state of our environment, and also a range of temperatures. And so then the way that we actually quantify how much hydrogen is dissolved in these samples is we use a technique called Fourier transform infrared spectroscopy, essentially taking an infrared spectra of our glasses. And so this is an example. This figure here on the right is showing you what our data looks like. So you're looking at infrared absorbance as a function of either wavelength or also wave number, either way. And the main feature that you'll see are these silicate glass features that are above around 5 microns or so. And the main feature, though, that we really care about and want to measure is this small little bump, right? Just shortward of 3 microns. And this is due to the OH stretching band. And so this is the way that we are going to quantify how much hydrogen has dissolved in our glass samples. And so we can use and apply the Beer-Lambert law to actually get a concentration of hydrogen. So this is now just zooming in onto that little peak that I just showed earlier. We measure the heights of these peaks, and then we can relate this to, in parts per million, how much hydrogen has dissolved. What's interesting about these samples, in every single sample that we have analyzed, we are seeing hydrogen dissolve exclusively as OH. So it is bonding with oxygen, either that's in the gas phase or oxygen that's already in our silicate, in the silicate melt itself. If we were seeing hydrogen dissolution in the form of molecular hydrogen as H2, which has been reported previously in some higher pressure experiments, we would see a peak right where I've sort of have this arrow, like a little bit above 2.25 microns, and we don't see that. So it's exclusively as OH. And I'm happy to chat also during Q&A about all the specifics of fitting for these different parameters that are in this law. And so another thing too, you might be wondering is, okay, you have this glass, are you just taking one spectra that's sort of averaged over the whole thing? How do you know that the sample is actually homogeneous? So the way that we're actually doing all these measurements and what each line here that I'm showing you is actually an average of a bunch of different points along our sample. So we're using an FTIR microscope for these measurements. This just allows you to take much higher resolution measurement at different points along your sample. So this is an example of one of our glasses that did have some iron in it. So interestingly, in this case, we're not seeing the full sample being homogeneous. We have a big portion of iron metal, which is the dark kind of cloudy material in the middle, and then everything else around it is our glass. And we can check that indeed the glass itself is homogeneous, and we see this, of course, with our other samples too. So then we take all of these individual spectra and average them in order to get our full amount of hydrogen in our samples. Okay, so here's what our results look like. So again, we looked at different compositions and temperatures. So I'm going to try and present all of that here, which is a little bit challenging in one plot. But so just to walk you through, both of these two figures are showing you the concentration of hydrogen, so in parts per million, that's dissolved in these silicate glasses as a function of the partial pressure or fugacity of water in the gas phase. And so remember, I did some experiments. I mentioned, we could go all the way up to pure H2, just a 1 bar of hydrogen. So in that case, we have very little water in the gas phase. So that's all of those ones on the far left. And then we also introduced some with mixtures of carbon dioxide and hydrogen that generates water. And so that's what you're seeing as the kind of middle and the far right points. And so what you can see is in all cases, the solubility of hydrogen increases as you have more water in the gas phase. This makes sense given that we're seeing hydrogen dissolve as OH. So the more oxygen that you have available, the more hydrogen that you can dissolve. And so then the top panel is just showing you one of the base compositions that we started with, also showing different effects of temperature by the color gradient here. And then the bottom panel is showing you for different compositions that we looked at, including samples with iron, which are the stars. I will also mention as a control and to sort of test our detection limits or potential for contamination. We also ran some experiments with pure carbon dioxide gas. So where there should be no or very, very little hydrogen at all in the gas phase. And so our data for those samples is indicated by the plus marks. So you see those are all quite low. They're all at most around 3 or 4 ppm of dissolved hydrogen. And so that we can sort of say is our detection limit for these experiments, or the maximum amount of contamination that we see. Okay, so then we take these samples and we'd like to quantify the effect that hydrogen solubility or how melt composition affects hydrogen solubility. And so one of the ways that we can do this is to look at the concentrations of dissolved hydrogen as a function of essentially how polymerized our melt is. And so there's different ways that we can look at this, and there's also different parameters that you could use here. In this case, I'm using what's called optical basicity. And so this is essentially telling us how interconnected the silicate network of your melt is. Another term that is very similar and behaves very similarly to optical basicity is something like NBO over T, so non-bridging oxygens divided by tetrahedrally coordinated cations. And so essentially what this tells you is if you have a higher value of optical basicity, that indicates that your melt in terms of the silicon oxygen network is less interconnected and the melt is less viscous. So this result was actually a bit surprising to us. We initially would think that if your melt was less interconnected, there would be more space for you to dissolve your hydrogen. And so that you would actually expect the opposite of what we're seeing here, which is that the amount of hydrogen that dissolves decreases as your melt is less interconnected. But one possibility to explain this is if we look instead at something called ionic porosity. And so this is similar, but not exactly the same thing. This is a measure of how much free space you have in your melt that's between ions. So it's not necessarily looking quite as much at the oxygen tetrahedra structure, but more how much, sort of vacancies that you have in our melt. And that behaves opposite to optical basicity. And so this does seem to make some sense or suggest this could be an explanation for the compositional dependence that we're seeing, which is that as you have more free space in between your ions in your melt, you can dissolve more hydrogen. So we're still trying to fully understand all of this, but this is a tentative result that we're seeing, is that there is indeed a compositional dependence, and it seems likely that it could depend on this space, the amount of space that you have between ions, with more space causing more hydrogen that can dissolve. And then we also wanted to look at the effect of temperature and also iron content. And so we do see a tentative increase in hydrogen solubility with temperature. So that's the figure that I'm showing you on the left. We performed several experiments going up to 1550 degrees Celsius, and we see somewhat, within sort of averaging of our different samples, a tentative increase with temperature. However, if you think about instead look at iron content, we don't really see any clear dependence of iron content influencing the hydrogen solubility. One of the other interesting things, though, that is happening in our cases where we have included iron in our samples, you might notice, okay, I have these three different points here with 10%, 20, and 30% FeO. But then what I'm plotting on the x-axis is much, much smaller than that. I'm only showing you 1 weight percent of iron. So what's actually going on here is that despite in our initial samples, which are homogeneously mixed, the material has 10 weight percent of FeO in it, in the experiment, and this is likely during the experiment, not just a quench effect, the fact that we're doing these under quite reducing conditions reduces the iron that was iron oxide in this melt to iron metal. And we see that with these kind of clouds, and we've tested these with microprobe analysis, and indeed these are just pure iron metal globs that have formed. And so most of your iron is trapped there. It's not existing in your melt. And so that is why the amount of iron that we actually measure in our glass is so much lower. So it's tentatively no major effect with iron. Okay, and so just to conclude on these experiments, the goal then is to take these and then put this together into a solubility law so that folks that are trying to model either magma exoplanets or thinking about early Earth, that you can use this in your model to say, okay, I have a planet with an atmosphere that has so much hydrogen. How much of that hydrogen can I actually dissolve into a magma ocean? And so this is what we are currently working on. The first thing to do is to think about what are the main chemical reactions that are actually happening in this system, where you have either hydrogen or, in some of our cases, we have water in the gas phase. How does that then combine with oxygen in the silicate melt to ultimately form this OH feature that we see in our infrared spectra? And so we think there's two main reactions that are taking place. In the case where we actually have some oxygen in the gas phase, we are producing water. And so then that water can react with oxygen that's in your silicate network and form OH. So that's the reaction in the blue box. And then the other reaction is, again, at some cases, we have no oxygen or very little in the gas phase. We just have hydrogen. And so that also is likely then going to react with oxygen and form your OH. And so if we take these two reactions, we can develop a law. This is basically following, assuming you have a chemical equilibrium reaction here, but we're trying to fit for some of the parameters that we have some control over. So temperature and melt composition mainly. And then we know there should be this square root dependence if you just work out from these equilibrium constants what you would expect in terms of the behavior of the amount that you can dissolve as a function of the fugacity or partial pressures of these species. And so what you're looking at here is our model using this functional form at the top, compared to our data for all of our different data points. And so this is not doing too bad of a job to fit our data. And we're still playing around with this, in terms of which compositional terms do you include, and likely would like to include a full, Bayesian approach to look at this so we can get a sense for which parameters are most strongly controlling your solubility. Okay. So that has been our work on hydrogen solubility. And in the remaining, 5-10 minutes or so, what I'd like to do is tell you about a different setup that can also tell you about volatile solubilities, also at around a 1 bar pressure condition. But this system can also do more than that and give us some spectroscopic constraints as well on high temperature melts. So this is a system that's been developed by Paolo Sosi and others at ETH, which is an aerodynamic laser levitation furnace, or ALLF for short, connected to one of these FTIR, so infrared spectrometers that we just were talking about. And so this is a photo of what the system actually looks like in real life on the right, and then a little schematic. So what this system does is it uses a carbon dioxide laser to heat samples from the top down. So it's going to heat your sample that you see circled here in orange. This can reach extremely high temperatures. So as opposed to the system that I was working with for the hydrogen solubility study, where you're limited and you can't go up much higher than 1600 degrees, that does limit you, especially if you're trying to think about different melt compositions, such as more primitive early Earth mantle-like compositions like peridotite. It causes limitations. So this system alleviates that. It allows you to go to 2500 degrees Celsius or even higher. And then the samples levitate through a gas flow. And our lab is equipped with all of these different gas species. You might be thinking, hydrogen, again, seems a bit scary given that this is all open to the air, and I assure you that it is diluted hydrogen this time, so it is safe to work with. But so then this flows gas up from underneath your sample, which levitates it. And then one of the very unique features of this system is that it has an FTIR spectrometer that is connected in situ. So this will allow us to take spectroscopic measurements. So in particular, it'll allow us to do both emission spectra. So this will allow us to get emissivities of compositionally diverse melts at the temperatures that we expect something like, say, 55 Cancri magma ocean to be at, and also transmission spectroscopy. So this is really interesting for trying to compare with our atmospheric observations, because this will allow us to get speciation of different species that are being released from different molten materials. And so here's a quick video just to show you what the system actually looks like in reality. This has a filter on it because it's very, very bright in person. And so you can actually see some of the gas being released from the sample. And so I'll show just some very preliminary results. So we've been working on testing the emission spectroscopy mode of this instrument. And so you can see here for different melts and at different temperatures, these are the sort of emission spectra that we're getting. This covers very similar wavelength range to JWST. So we can go from about a half all the way to 20 microns or so. We are having to correct for the atmosphere's spectra because currently the system is completely open to the air. And so some of the major dips that you see and features in this particular spectra are just due to features in the air like water and carbon dioxide. And then we are also in the process of testing things in transmission as well. And so this right now is not looking at outgassing from any particular sample, but just from looking at our gas flow. And so we can indeed confidently detect carbon dioxide when we're flowing that through our system. And I should mention, this gas as well is diluted. So it's not just 1 bar of CO2 that we have coming out. This is lower than that, and we also had to correct for atmospheric contamination. So stay tuned for more results here, and if you have ideas for compositions that would be particularly useful, especially for the people that are trying to interpret observations, we would love to hear from you. Okay. Now, these experiments are really great, and putting these solubility laws together are really important, but we need a theoretical framework to ultimately use all of this knowledge to actually simulate what we would expect a particular rocky magma planet's atmosphere to be composed of. And so this little schematic here shows, roughly speaking, of course, that we have these magma ocean atmosphere interactions. And it's really important that we can understand what's going on with the chemistry at the atmosphere melt interface. And then using that information, of course, this needs to be propagated upwards and throughout the rest of the atmosphere, looking at things like full radiative transfer codes so you can simulate the spectra that you would ultimately observe. So what I'm going to focus on is a code called Atmodeller, which will allow us to understand the partitioning of volatiles for either a solid or molten surface. It's really going to tell you what's going on right at this interface. And so this code has been developed by Dan Bauer, who's at ETH. And it is a chemical equilibrium code that will include multiple things. First, condensed, so both melt and solid phase thermodynamics. It includes solubilities of a variety of different volatiles, all of the major species in the CHONSP chlorine system, helium as well. And in particular, it includes the compositional dependence, which I think is quite important to be sure that we're being consistent. If you're simulating a planet and you want it to have, say, a basaltic composition, that then all of your solubility laws are consistent with that composition. And going back to this thinking about whether rocky planets, or even as we go into super Earth, sub-Neptunes, of course, we can't just think about them as only having outgassed atmospheres. It's likely that there's going to be a combination with some hydrogen atmosphere or primordial envelope in there. And so you could get to quite high surface pressures in these cases. And so this code also includes the effects of non-ideality. So when you get to these high pressures above a kilobar, several GPa, it's important to consider real gas equations of state here. And it also includes condensates. So highly recommend, getting in touch and chatting with Dan about this. I will just leave this up here briefly, but these are a lot of more details about the code itself. But there's a lot of tutorials and test suites. So I would say it's very, very user friendly. So feel free to check it out and get in touch with Dan if you would like to try out using this. We've also been able to benchmark it against various software that already exists. So for example, FactSage, which has been important for validating all of our results. Okay, and so again, I'm showing you this figure of all the different solubilities just to show this is something that is already incorporated in Atmodeller, but also if you have a different solubility law that you would like to include, that's one of the real benefits of this code is that it's very flexible to just being able to add in new solubility laws or new equations of state. So on the right here, I'm showing you some of the equations of state that we've included for several carbon species. So when I say real gas equations of state here, I'm talking about in the regime where you're at high enough pressures where now we can't ignore the fact that gas molecules are actually going to interact with each other, and they actually take up an appreciable amount of the space. And so we often use fugacity coefficients, which is fugacity divided by pressure. We use that to describe these non-ideal effects. So once you get above 1, where your fugacity is then higher than your pressure, you're in this regime, this non-ideal regime. And so this varies, of course, depending on temperature and also total pressure, but these are included in this code. And so just to show some of the results and how doing solubility experiments can be important and then be fed into a model to actually simulate something like, say, TRAPPIST-1e or a various exoplanet that you care about. We use TRAPPIST-1e just as a test case. We said, let's pretend like we're looking at TRAPPIST-1e much earlier in its history when it was very hot. Say it had a magma ocean in its early evolution. So we're giving it a surface temperature of 1500 Kelvin. I know that is not what it likely currently has. So this is just thinking about it in an earlier phase. And the top figures are showing you the results where you do not assume there's any solubilities. So you probably have a bit of a molten surface, but you're not including the fact that you could dissolve some of your volatiles into the melt. So it's really just chemical equilibrium at this point. So you're looking at volume mixing ratios as a function of redox state. So further to the right is oxidized, further to the left is more reduced. And so you end up with, if you're more reduced, a lot of hydrogen, you're more oxidized, a lot of water. That's your dominant species. You also have some some much more minor amounts of carbon species and even more minor amounts of sulfur. But if you do include solubilities, then the situation is drastically different. You no longer have a water-dominated atmosphere. And if anything, no longer even hydrogen dominated. In very reduced cases, you can still have some significant amounts of H2, but all of your water is pretty much dissolved. Water is extremely soluble in typical silicate melts. So instead, you're going to be carbon dominated. And so this can have a really profound influence on the species that we would expect to be in these planets' atmospheres, and also what this could say about sort of the long-term volatile retention of a planet like TRAPPIST-1e, if it's able to dissolve a lot of hydrogen into its interior. What are the implications of that for its subsequent evolution and ability to retain an atmosphere and degas over time? And so finally, just to show that there's some effects that we can also see with thinking about sub-Neptunes. So we did a few simulations thinking about K218b. So this is sub-Neptune. We assume it has some sort of thick envelope overlaying a magma ocean, essentially, with a very hot 2000 Kelvin melt atmosphere interface. And just to show, if you assume an ideal gas, you will likely predict a very, very high total atmospheric pressure compared to if you include real gas equations of state. And so that's what you're basically seeing here, is just to see, especially in the lower panel here, that the pressures that you would conclude, assuming ideal gas, would be much larger than what you would actually get when you include these real gas equations of state. And lastly, this also influences your ability to store volatiles in the interior, because ultimately its fugacity is the thing that controls how much of a particular species you can dissolve into the interior. So if you're under real gas conditions, your fugacities are higher, and so therefore you can dissolve more of a particular species under a different range of conditions. So that's showing here. Again, the plot on the left is basically just what I showed you, that the total pressures will be smaller if you assume real gas. Then on the right, what you're looking at is the fact that you can have at higher fugacities, then your interior is able to store more volatiles compared to if you assume ideal gas scenarios. Okay, so I have some questions, and I would love to discuss these with you all. I will admit that a couple of them are kind of more experimental, and a few are more science-based. So I'll briefly say these, and then we'll open it up for discussion and questions. But one of the things that we've been thinking about a lot in Paolo's group is, how do volatile solubilities of change if they are in the presence of other volatiles? So a lot of times we do these experiments under very isolated conditions. In my case, I was doing hydrogen solubility with hydrogen gas, CO2. Carbon's not super soluble at these low pressures. So it's a fairly isolated system. And this is also how a lot of these solubility experiments are done. But say, for example, you have sulfur in the system. How does that influence your hydrogen solubility, and vice versa? I also think it's interesting to think about how can we use stellar abundance data and then models to simulate what we might expect for bulk rocky planet compositions for exoplanets, and how do we really use that information well? So if we're trying to simulate diverse compositions in the lab, what's the best way that we do that systematically? And then my two sort of science questions are thinking about this ability for a planet to in-gas some of its in-gas hydrogen as a source for volatiles and even potentially water over time. Will the planet actually be able to retain that in-gas material once its magma ocean has crystallized? And then, of course, lastly, for at least magma planets with observations, how do we take the observations that are probing upper regions of the atmosphere to actually infer what's going on with the planet's interior? So I have some thoughts on these. I will leave these up here and we can talk about it. And yes, happily take questions.
Thank you so much, Maggie. Let's virtually thanks, Maggie. Online claps. That was really fascinating, and luckily we have plenty of time for questions and discussion. I see a hand up already. Yeah, and if anyone else has a question, just raise your hand on Zoom. Shanul, please go ahead.
Hello, can you hear me?
Sounds good.
Yes, hello, thank you for the very nice talk. I'm Charles of National Astronomical Observatory of Japan. I have two very naive questions because I'm really interested in the hydrogen solubility to the silicate. And may I have missed your points in your explanation, but first thing that I want to ask is that when you see the Hirschman's 2012 hydrogen dissolution papers, they see some H2 signals from the quenched silicate. So I understood that hydrogen gases dissolution mechanism to the silicate is more governed by the physical dissolution of the H2 gas to the empty space in the silicate. But after I seeing your experimental result, it looks like that the hydrogen gas dissolves into the silicate as a chemical dissolution, which react with the non-binding oxygen ions or something in the silicate, like OH, so the form of the OH. So do you think that this kind of dissolution mechanism of the H2 gas is really governed by the pressure or something?
Exactly. I think that you're right. It's the pressure. So my understanding is all the studies and in particular the main one that I know of is Mark Hirschman's study back in 2012, where at higher pressure, so you need to get beyond 1 bar. I think his were several GPa. At those high pressure conditions, they do claim to see it dissolve as H2. So I agree that I think the pressure, the total pressure, will have an influence on what dissolution mechanism is taking place.
Okay, thank you. And my next question is related to your the code Atmodeller. Am I right? The
Sure, sure.
pronunciation? Yeah.
Sure. Atmodeller is all good.
Yeah, it looks, but you know, I think you're already aware that for the sub-Neptune surface pressure range is about it easily exceeds several gigapascal range, which is the experimental data. There's no experimental data for such high pressure solubility gases. And what I understood is that when I just extrapolate like Hirschman's hydrogen solubility low to such high pressures, the volume change term of the reaction makes the very unrealistically small solubility of the H2 gases. So I want to know what is the pressure ranges that water can cover and how you deal with such kind of extrapolation problems of solubility equations.
Yes, that's a very good question and something that we have been thinking about a lot. One of the things I will say that's really nice within Atmodeller is that we do are certainly document and then also have some ways to sort of throw warnings at the user when you are giving it. Yeah, exactly. If your total pressure is going to be beyond the range at which we are confidently extrapolating with these solubility laws, I agree with you. I think that it's challenging to know exactly what to do. I mean, I think for certain, this is why, partly why I had that figure with all the different species and sort of you can see how their solubilities change. I think, if it ends up with a particular law predicting that your solubility would just, skyrocket, that's probably
Yeah.
a problem. If it's just sort of plateaus, maybe then it's okay. I mean, I think ultimately we need more experiments. Something like hydrogen, my understanding is it's really challenging when you start getting into several GPa, tens of GPa, especially because the hydrogen just diffuses out really, really fast. So that quench process that I told you about is it's not fast enough. Like it still ends up, your hydrogen escapes too fast, but hopefully we can get some more experiments that help us. Maybe we can go to really high pressure ranges with like diamond amble cell experiments, and then we could then, might be then it makes more sense to sort of extrapolate in the in between. But I mean, there's also, simulations that people do, at least for thinking about real gas equations of state. This is something that others, do is they look at ab initio,
Oh, yeah.
simulations. Yeah, I wish I had a better answer, but I agree with you that it is challenging and yeah, like we have to be careful when we extrapolate.
Yeah, no, thank you for your opinion. Yeah, I always feel like there's such kind of constraint when I do model such high pressure magma atmosphere interactions. Yeah, yeah. Thank you for your answer.
Yes, of course, of course.
Since I don't see any other hands up straight away, I will jump in and ask a question as well on the hydrogen solubility. So it's really interesting to see that the hydrogen is dissolving as OH. I was wondering what implications does that have for outgassing later on, if it outgasses? I know is what like one of your questions. Would that outgas as H2, H2O, something else? Can it interact with other parts of the magma ocean or do other things?
That's a great question. That would be something that I would love to be able to explore, of course, more from the modeling side. Although actually, we probably could take these glass samples that have it dissolved as OH and then degas them and see what we see. I mean, my hunch would be, of course, it does depend a bit on the general redox environment that you have. That will dominate your speciation, but it does tell us that, ultimately you could view these experiments as almost water solubility, right? Like, I mean, aside from in the case where I have pure H2 in the gas, where we're still actually trying to think about exactly what's going on there, which free oxygen is it bonding to? But ultimately, it's just demonstrating this basically water solubility, how soluble water is, and if you can form it in any form, then it will ultimately dissolve.
That's really
Yeah.
interesting. Well, I see Claire has a hand up. Go ahead, Claire.
Hi, yeah, thanks Maggie for this really great talk again. My question is, I'm not sure if this is really something that you have been able to look at in your work specifically, but so I'm guessing that once you start the dissolving volatiles in magma, the magma is always becoming less dense because it has volatiles in it. So is there a way to kind of, if you like are dissolving stuff from the top down, to kind of get that into the deeper planet and kind of put that hydrogen into the mantle or something like that? Or is it difficult to do that? Like basically, can you kind of address the distribution of hydrogen through the planet?
Yes, I think that is an excellent question. Also, of course, applies really to any of these volatiles. This is actually something that we've been thinking about recently in the context of Atmodeller. And if you think about these, especially, kind of more like super Earth sub-Neptunes, if you end up to the point where you have dissolved so much hydrogen or water, whatever it is, that you can't just assume that the mass of your planet is and the radius is fixed anymore, because those volatiles add to it, and you can't just assume it's not that much and it's negligible. I think and I'm blanking now on which paper has looked at this, but I do know that there have been some studies done to try to simulate, okay, how are you actually then going to transport this stuff further down? I think it's important, certainly also if thinking about do we actually end up sticking volatiles into the core, then we need to have a way to get them from the top all the way down. But I think just as a first order, one of the things that we've been thinking of is how do you, especially in a modeling scenario where often you just sort of treat these solubilities as like, they're going in there, but the main impact is just that they're taking volatiles that could be in the atmosphere into the interior, but you assume the planet itself is not altered too much. But I think for these some sub-Neptunes or super Earths, we can't really make that assumption anymore. And we need to include the fact that then the size of your mass and size of your planet changes. So I basically don't have an answer for you aside from like, I completely agree that this is something we have to think about. And yes, hopefully we can do this with some simulations. If you get to maybe there's a threshold, right? You get to a certain point where you have so much volatiles that then at that point, okay, we now need to adjust the planet mass but transport, I think, would be very interesting. I think it depends also on like convection, how much, what's the convection situation like on these magma planets? Because
Yeah, totally. Yeah, thanks for the answer. I think this kind of maybe addressing like point 2 of your science box.
Yeah.
But yeah, I agree. It probably takes some like fluid dynamic seed type numerical modeling to do this, but I think that'd be like a really cool thing to look at.
Exactly. I agree.
Cool. Amy, go ahead.
Yeah, thank you, Maggie, for a really nice talk. I just wanted to touch upon how if we're in a different star system where the bulk composition is really different, like are there particular elements that you think are going to really influence these kind of results, or is it just anything could happen?
Oh, absolutely. I mean, this is where I also, the phase space that we could look at is so large, right? That and like unknown. I mean, I think one thing that would be really interesting, and this is actually something that one of Paolo's PhD students, Urja Severi, has been working on, is thinking about if you have a much more chemically reducing system. This is really just actually going all the way back to thinking about nebular condensation. You know, if you have a system with, you know, very carbon rich host star, how does this then influence which species should condense? I mean, I think looking at these sort of extreme end members would be where I would be interested. And I think at least, you know, if we could try to bookend things a bit, that's probably the best way to approach it. This is why I think, you know, looking at something like hydrogen solubilities in the presence of really reducing plus carbon rich systems would be interesting. Although carbon is not super soluble, so you know it's unclear whether that would have a huge effect. Also sulfur, but yeah, it's a fast parameter space. I would just say probably if we look at the most reduced and oxidized possible end members would be a roughly good place to start. But even within that, I know there's a lot of uncertainty.
And that's hard because so like we can observe stars, right? And we can get compositions for individual systems, but within that we can't tell how reducing or oxidizing an individual planet might be, right? So
Yes,
you're always going to have that free parameter, even when you're in a world which has low phosphorus or high sulfur or whatever.
exactly. Like maybe we start and say, okay, let's just stick with solar abundances, but you know, we look at something like Mercury that is so reduced. You know, how would things look different in a scenario like Mercury?
Does magnesium with silicon make a big difference? Kind of magnesium to silicon, does it dominate the mineralogy, or is that not important?
Yes. So in the figure that I was showing, versus you know, you have hydrogen concentration versus optical basicity, or you know, something to sort of get at the polymerization of your melt. The samples that were quite soluble are ones with a lot of silicon. They're the ones with additional quartz, so they have a lot more silicon in them. So I do think that that's part of the goal right now of this model, is to tease out, yeah, is it silicon and magnesium that have the main influence? Does calcium also matter? You know, that's my the hunch is probably yes, like it's, yeah, probably silicon and magnesium, and maybe also calcium too.
Okay, that'd be really interesting to see. Thank you.
Yeah, of course.
Great. Do we have any last minute questions? I don't think I see any other hands raised right now. If so, maybe we can thank Maggie again virtually. This is really fascinating. Thank you for sharing your work with us. And next month, we will have Jane Birkby as our speaker. Jane is actually here today. Jane will be talking about Jane will be talking about rocky planets in high spectral resolution, and that will be at 1 p.m. UTC next month in November. So thank you all so much for joining. Thank you, Maggie, for a wonderful talk, and we will see you again next month.